Now, okay, hey guys, welcome to week 3 of Techquitable. This week, we'll be going over topics of complexity analysis, technical question approach, and arrays. Yeah, which is also listed here. But before we dive in, Viveka, do you want to also give a quick introduction of yourself?
Sure. Hi, everyone. Great to be here with you all this Sunday. My name is Viveka. I am currently a software engineer at Square, and I'm also a program manager with Techquitable. So yeah, that's kind of what I've been doing. Really excited to do this lesson. This is my second cohort as a mentor as well.
Thanks. Yeah, thanks for that introduction, and thanks for joining us for today as well. And as you guys know, also presented last week, but my name is Wentao, and I'm happy to join you guys once again today. All right, let's get started. So the first topic is going to be on time and space complexity. Sounds pretty complicated and a little spooky, but no worries. So why are we going over this today? So the motivation for this is that this complexity topic is asked in like most algorithm and data structure questions. And why interviewers ask them is that it's used to kind of evaluate foundational computer science knowledge. And a lot of companies like also make this like understanding of the complexity like a requirement in passing the technical round. So this is why we're going over them. And now to kind of like dig into the definitions. So what is time complexity? Time complexity measures the amount of time taken by an algorithm to run as a function in the length of the input. If that sounds a little still complicated to you, no worries. All it's saying is that it means the amount of time your code is going to run in comparison to how big the input is. So that's what time complexity is. And space complexity is similar, but now instead of time, it's looking at space, or in computers, like architecture is the memory. So this basically is like measuring how much space or memory would your program require in relation to the length of input. So this is just a sample, but let's say that you're given an array A and an integer X, and you have to find if the element X exists in a given array. Well, the solution should be pretty straightforward, which is you can have like an array and you can iterate through them and try to see if that each element is equal to that element X that you're looking for. And I'm going to dive into just analyzing the complexity of that in a moment. But to kind of describe how like the time complexity grows, there are like 3 main notations that we use in computer science. One of them is called the big O notation. The second one is called big omega notation. And the last one is called big data notation. In technical interviews, like big O notation is the one we really care the most. And what this tells us is that it tells us like the upper bound, or basically the maximum amount of time in the worst case scenario that your code could take to run the program. So how do you calculate it? Well, just to use an example, it's pretty straightforward, which is that you can basically ignore the low order terms, since the lower order terms are going to be insignificant for like a larger input. And the higher order term is like what's going to dominate your runtime. So this is just like a purely mathematical example, but let's say that you have like this like function that has like this like expression that goes like 2 times n squared plus like 3 times n plus 5. But if you like really kind of like describe this in like a big O notation format, what happens is you start to kind of ignore just like any low order terms here. So obviously you kind of like ignore this like plus 5 component, because like that's like what's considered like a constant. 3 times n, you also ignore that. Why? Because there is a high order term, which is like the n squared, right? So that 3 times n you can also ignore. And in the end, you're kind of like left with like 3 times n squared. But that 2 in the front, you could also ignore it as well, because that's just a constant multiplier. That kind of gets applied to the highest order term, which is n squared. So in the end, you have O of n squared. That would be a runtime, right? And why is that important once again? Well, it really like impacts your runtime depending on like what complexity your code has and how big the input is. So in the ideal scenario, like your code could just run in like O1. And you notice that there's like no term of n here. And that's because what this is saying is it doesn't matter how big your program is. Your program could run in like a constant time, right? So that's very fast. Like it doesn't matter that your input has like 1,000 or million or billion. It doesn't matter. It's going to run in constant time, right? So that's kind of like the best like runtime that we could ever get. And then there's like a log n. Log n is nice because there's kind of like a log that gets applied, and that could like really reduce the runtime in comparison to the size of n. So just to use an example, like let's say we have an input size of 8, right? When you apply log, the kind of like the implication here is that the base is like it's using a base of 2, because it's like in computer it's using bit. What happens is like, okay, basically kind of goes to like this halving mechanism, right? So 8 kind of goes to 4 in like this like one halving, right? And then 4 goes to different, and then in another halving, it goes from 4 to 2, and third halving goes from like 2 to 1, right? So that's kind of like how like the log would work in that case. And instead of like going through like 8 elements, now it would only have to go through 3. Now like that, operation like 8 and 3 doesn't seem that much of a difference, but imagine like this is like a million, right? Now, like instead of like doing a million times, like log n would do it in like a much like reduced runtime, right? And then lastly, well, not lastly, but there's also like O of n, which is what we call the linear runtime. We kind of see this often. For example, iterating through an array is like usually like a runtime, right? As long as that operation inside that, each iteration is like also constant. Yeah, so that's kind of like, what we often see as we kind of iterate through like what's known as iterable. Iterable could be things like array, object, and so on. And then there are also like, a lot more like slower cousins in this like kind of big O, charts, right? So there's like n log n and n squared. I'm not going to cover it all, but n squared you guys might see in like a kind of a nested for loop, right? Like there's like an outer loop that's running n times, and then there's could be like an inner loop that's also running that could be also running O of n. When those two gets multiplied together, they end up like in O of n squared, right? So this is why like runtime it's important to know like the runtime, because it really impacts your how fast your code will run. So once again, to kind of get back to the sample problem, like in this sample problem code, what it's doing is that it's basically counting how many elements are in the array. And I would like to just ask everyone, but can anyone tell us like what the runtime of this will be?
Oh, then.
All right, oh man. And that is correct. And that is the right answer, because the count is getting incremented for each number from 0 up to n, right? So that's why, and then this counting operation is like also done in constant times, and then we're doing that n times. So the runtime of that is O of n. And now moving into the second sample problem, like to kind of like ask this question to everyone again. But what will be the runtime of this? Anyone? Maybe I can ask on IO.
O of n squared.
Oh, okay, Oriana, you got it. It's O n squared. All right, and then do you want to explain to us why it's O of n squared?
Because of the double for loops.
Double for loops, right? And then double for loops, and then kind of like the operation that's being done inside that like inner loop is also like done in constant time, right? So that's why it's like constant time times like n times n, right? That would kind of like end up in like n squared. So, and yeah, that's the right answer.
Are there times when there's double for loops and it's not n squared?
Yeah, so you could imagine that if like the operation that's being done inside like the loop is getting run in like a different runtime, right? Like instead of like, let's say counting here, we're calculating the sum of like all the elements in that like array or something, right? In that case, like calculating the sum could also be like an O of n or linear time like operation. And if we're doing that n square, even though it's like a double nested loop, it could end up in like a n to the third power or like n cubic runtime.
Thank you.
Yep, but that's a good question though. Excuse me. And then lastly, this is a little tricky one. It's similar to the second sample problem, except if you look at the inner loop, instead of like going from like for j in range n, which means like going up from like 0 to n, it's basically like doing from like for j in range I, which means that it's basically starting counting from like range I. And I, in this case, is getting set by, sorry, not counting from range I, counting from I. It's basically like this range function ends at this element I, and this element I is being set by this like auto loop. So it's not quite doing the same thing as the last one. If you, for comparison, this like inner loop goes from like 0 to n, right? But then this one goes from 0 to I. So it's a little different. And I'll be curious to know if anyone knows the answer of what the runtime of this is.
Is O of n times I.
Oh, okay, Darren, can you repeat your answer?
O of n times I.
Oh, n times I. That's, yeah, that's a good guess. So you think it's O n times I because this I, because you think, okay, so it's getting like, this inner loop is doing like I times number of work, right?
Yeah, but I know I is like increasing every time, so but I'm so not sure how to like model that.
Yeah, so I is dynamic, right? It kind of gets
Mhm.
updated each time the outer loop goes to like the next element. Yeah, so how should we model that?
Is that I factorial?
It is not I factorial. The kind of like the best thing to do here is just to kind of like maybe like think through in your head like what the first example is going to be or first iteration is going to be, right? And we can do that exercise together here, which is when you first run this, I is going to be 0, right? So then the inner loop is going to be for j in range 0, which means that it's actually not going to get run because 0 to 0, there's like no elements in between, right? So then it kind of gets skipped over. But then in the next run, the I is going to be set to like 1. And then now like this inner loop is going to go from like range 0 to like 1. So it is going to like count the 0 element. And then, so then in this case, like J would, this inner loop would actually run and then the count will be incremented up by 1. So that's fine, but then it's going to just stop running there because when you have like range 0 to 1, well, this is like kind of using like a Python pseudocode, but it doesn't count the end index, or it doesn't include end index. So then it kind of goes back to the outer loop again. And then I gets now incremented to like, let's say 2. And then the inner loop is now going to run like, both like run over the element of 0 and 1. So now it's going to count 2 times. And if you kind of repeat that process, in the first iteration, we counted 0 times. In the second iteration, we counted 1 time. In the third iteration, we count a second time. And in the fourth iteration, we're going to count 3 times. And it's kind of keep going like up like that until the other loop like hits this like, n element of like n minus 1, right? So if we were to kind of model that, it's a little complicated, but then kind of the end solution here is still like O of n squared, which is once again actually similar or the same as like the answer to the second example problem. And the reason for this is like, as I was kind of trying to illustrate, we kind of like count like more each time as the other loop kind of gets incremented as well. And then when we kind of express it in this like mathematical terms, like what you have is like you have like 0 plus 1 plus 2 plus like dot 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 all the way to like n minus 1. And what that means is that there are basically like n over 2 number of terms of value where the value is equal to n minus 1. This is like a little trick where you do like where you add the first number and the last number together and they match up to be like n minus 1. And if you were to like add the second number and the second to the last number together, they also add up in the same number of like n minus 1. And what this is saying is that because like we pair up 2 of them to like form this like one value, we started out with like n number of terms, but because we're pairing 2 of them together, it's going to end up with like n over 2 number of terms, right? So then what we do then is then we multiply them together, and what we have is like n squared over 2 minus like n over 2. And then finally to kind of like represent this as like a big runtime. Once again, you know all the lower order terms, right? So you just kind of like, in the end, still focus on this like n squared term, right? So that's what we eventually end up with. So it's a little counterintuitive because you think, well, wait a minute, isn't this like doing like less work than the last example? And the answer is yes, like technically, like, or like realistically speaking, like that is like actually doing like less work. However, like when you represent this in like big data or like big O notation, this actually ends up being the same. So yeah, just like something to kind of like illustrate, and then what you've got or what intention is telling you may not be true until like you actually try to calculate things out. So all right, so that's the time complexity part. But does anyone have questions about this?
I do have a question. So could you go over the like how like the n minus 1 and there's n over 2 terms in the n minus 1 again? I guess I'm still kind of confused on that.
Yeah, so this is like a kind of like a mathematical trick, right? Like so this like 0 plus 1 plus 2, this each of the value here represents the number of times you're counting or doing an operation in this sample code, right? Does that part
Yes.
make sense? Okay. So then the part about this kind of like adding the 2 numbers together and how they're like n over 2 of them. So what happens is you add the first value and the last value together. You pair them up together, right? And they add up to be like 0 plus like n minus 1. Well, that's the last term. So the value, the sum of those two the 2 values is n minus 1. And what you do is like, there's actually a pattern like where you also add then the second value and the second to the last value. The second value here is 1. The second and last value here, although it's not shown here, it's supposed to be like n minus 2. So when you add like n minus 2 plus 1, they also still add up to be like n minus 1. And you can kind of keep doing that and like and do like add up the third value and then the third to like last value, which would be like n minus 2. Oh, sorry, n minus 3. So and then and 2 here, they will still add up to like n minus 1, right? And then because each pair adds up to like n minus 1, And then when we ask ourselves, okay, well, how many of those n minus one values are there? Well, we did start out with like n number of values or terms, right? But because of we're pairing them up two at a time, you're dividing that by two. So then that's why how you end up with like n divided by two times like value of n minus one. So gonna take a pause here, but does that part make a little sense?
Yeah, it makes a little bit more sense.
Yeah. You can also kind of like, do this, kind of like, it might be easier to kind of like draw it out with like using some numbers from like, let's say like 0 to 10. And you start like kind of like doing this like arcing exercise to like pair those like numbers together, the first and the last value, and then the second value to second and last value together, that you can actually see that, oh, each of them actually like adds up to the same number. And there are going to be like n over like, two number of terms there.
Got you. Thank you.
So then, and then as you multiply them out and you apply this like big O notation, you kind of, once again, you drop all the lower order terms. So then in the end, what you really care about is like n squared over two. Over two, like this basically means like it's being multiplied by like 1/2. And you can also like kind of ignore like all the multiplicative factors that are getting applied to the like in any kind of like n terms, right? So then what you still end up with is like O of n squared. And then the kind of the last point that I'm trying to make is that in practicality or in reality, this code is like slightly faster than the last one, just because it's like doing like less work. But in theoretical, like this like big O notation, because we're like doing this kind of like what big O is telling you is, okay, what is the worst case runtime? And that theoretical answer is actually the same as like the answer to the last sample problem. Little, is it better now in terms of understanding?
Yes.
All right, sounds good. All righty, now we're gonna move on to the technical question approach, which will be presented by Viveka.
Hey, everyone. Yeah. So in the previous week, we talked about kind of how you want to approach, like, for example, resume writing or behavioral interviews in general. And of course, over the course of this program, we will be talking about different types of technical problems, but all of them can kind of be our technical problems that we want to think about approaching in similar ways in terms of the method. So this is what we're going to, before we dive into our specific area, which is going to be arrays, we're going to talk about just approaching a technical question just from the very beginning. So, of course, we know we've also been there solving technical questions in real time in front of someone else who you probably don't know. Can feel like a lot of pressure, can feel very stressful. And oftentimes I find it's not always about whether you know something or not, it's just being able to set yourself up for success. Because if you don't know it, you can work through it, but you need to be able to have a system which is going to be more helpful working through it, especially if you're not sure at first. That way you have a method you can follow to help you solve the problem. And this is something that, as you practice it, will continue to be helpful in lots of different technical problems. So we can break down the system into these 5 steps when you're given a technical question, the things you want to make sure you're doing and you want to follow. So of course, the first thing you're going to want to do is ask questions. And the kinds of questions you're going to ask are basically making sure you really understand the problem and its limitations and what is expected of you. So that might mean asking about certain kinds of inputs, how you want to deal if an input is not valid or something. Like if someone asks you to do something with a string, you might ask, well, what if the string is empty? What should I do then? That's an example of an edge case, for example. And that you just really want to make sure you have basically everything you need. And it never hurts to clarify something. Even if it feels obvious, just to make sure you can always repeat back the problem. So here we have an example here. A lot of this, and this is really important because it makes sure you're able to kind of ask and drive your understanding of the problem yourself and figure out where those points that may be unclear are. So here, let's say you are asked to find the oldest person in some list of inputs. So the first thing you're going to ask is, well, what kind of input is it? You know, they may have already given it to you, but if it's vague, that could it come in a lot of forms? Excuse me, it could be an array, could be a hash map, could be some other kind of data structure. And then thinking about the input, what could make your output, your desired output, be a little more unclear? So for example, if you have multiple people with the same age that are also the oldest, what do you do? And that could be up to the interviewer. Maybe they'll say, return everybody with the oldest age. Or maybe they'll say, oh, just return the first person you find with the oldest age. That could be up to them, but it's very helpful and it's going to have an effect on the algorithm you are trying to write. And then of course, also, can we, there be multiple people with the same name? You're going to want to handle that input. If that is the case, if that's a problem they say you should be worrying about in this question. So the next thing is, of course, designing the algorithm. When we say design, we don't really mean code. We really mean think through conceptually how are you going to take your input and get to your desired output? And really what was going to serve you best here is identifying the brute force solution first. And we talked, Wentao has talked about time and space complexity. And that's a great way to kind of evaluate once you have an algorithm. Okay, do we feel like this is the best we can do? But honestly, in most cases, when you have an interview, really they want something that works, because that can show that you can think through a problem and get to a desired solution, as opposed to something that might sound really sophisticated and fancy and really speedy. But if you're not able to take that all the way, you're not able to actually confirm that solution will work. So a brute force is always going to be better than nothing or a non-solution. And you can always optimize it later. So especially if you're not really sure about the best way to go through the problem, brute force is definitely the way to go. And then, of course, as we say here, once you have brute force solution, you can go and optimize it. And that is where the time and space complexity is going to go. If you are able to calculate that and say, oh, okay, maybe this is n squared right now. Can we get it for space? Can we get it down to n? Something like that. But of course, again, I really want to emphasize here, this is once you have the brute force solution, you're able to make those kind of updates. And really quick, right before that, you can always ask as well with your interviewer, once you have brute force solution, before you put it up, you can always say, okay, here's my brute force solution. Do you want me to code it, or do you want me to write it up now, or do you want me to think about how to make it more efficient? And the interviewer will often kind of push you in the direction if they're more interested. If they're fine, we're like, okay, yes, we understand the solution. How can we make it better? Or no, we want to see you code now. So it never hurts to always be asking questions from the interviewer to make sure you're on the same page. So for step 3, you're going to want to start writing pseudocode. And this often is very helpful because sometimes maybe you've talked out the solution. Maybe you don't have a lot of notes. You just kind of have this concept of your brute force algorithm in your head, and you want to translate it to code. The pseudocodes or the comments really help to organize your thoughts and can help bridge that gap between kind of ideas, concept, words, and actual code. So here's an example here. You want to find the oldest person. You have your inputs right here. And you can comment, okay, these are the steps we went through. Build a hash map, the key value pair, and then we're going to iterate through. And then, of course, you can always put the code for those comments in there, and that will kind of help keep the momentum going as you are working through your algorithm. So then after that, you're going to want to write the actual code, of course. And this is where your comments have really helped you, so you can follow in after that. So we want to build a hash map. Okay, we're going to define our hash map, and now we're going to populate it, going over the people. And you can see we've actually left the comments here because it's just helpful to help us keep track of what's going on. Make sure that when you go back, your comments are really your record of the algorithm you've come up with so far. And you can always check back and make sure, okay, this is the code piece that goes here that corresponds to, for example, go iterating through the hash map. And then after that, you're going to want to test your code and fix your mistakes. Oftentimes in interviews, interviewers might ask after you're like, okay, I've written the algorithm, and the interviewer might say something like, okay, what do you think about it? Or how do you feel about it? And that can be a little bit of a nerve-wracking question. But often what they mean is just how confident are you in your code? So you can always try running your code with test inputs. And if you're working in like an online IDE, like a collaborative tool, which, because of course, most interviews are going to be virtual or over the internet, that's going to be an option. You can always just plug it in, but it never hurts to kind of go through it mentally and talking it out. Like, let's say the input was 5, and then walk through it and maybe take some notes or comments, put some comments in before you actually hit run on the code. That can be a really great way to check things really quickly. But let's say you want to run your code. If it doesn't compile, or you have a runtime error, or it just doesn't come out with the answer you thought it was, do not panic. This can often be really helpful for interviewers because bugs happen no matter how much experience you have. So whether you're in an interview or whether you've been working for a decade or longer, bugs happen, and debugging is part of the job. So if you do have a bug in your code or something doesn't work, go through as you would try and figure it out. Read the stack trace, read the error message, see if you can go back in the code to where the issue is, if it gives you a line number or something. And it can also help to talk out what you think the problem is, how you think you're going to fix it, and you can continue to test it that way. And that actually can be really helpful if you are able to find a bug and then talk through what you think the issue is. That is even more signal for the interviewer to say, oh, okay, so they don't just have to write perfect code all the time. When they have an issue, they're able to think through what it could be. And then, of course, when your code does run correctly, you can think about how you can write even more test cases or edge cases to consider your different inputs and how your algorithm will deal with that and make updates if necessary. So that was kind of, I understand that was a ton of information there. We, of course, will be sending this info out so you can refer back to it. Really recommend going through the system in general, just to make sure you kind of cover your bases as you go through the problem. Does anyone have any questions?
Yep, and then once again, the 5 steps are listed here. Step 1 is to ask questions. Step 2 is to design an algorithm. Step 3 is to then write a pseudocode or comments that will kind of like help you write down some of the thoughts that you have. And then step 4 to actually just translate those pseudocode or comments into actual code. And lastly, test the code and then fix any mistakes you have. But if there are no questions, then I'd love to move on and actually apply this in practice. So moving on to this topic array. In a moment, you see how we're going to apply this to like a sample problem, but that's before we dive in. We'll kind of like learn a little bit of arrays, or just a quick overview. So what is an array? So array is basically a simple data structure that represents a collection of items. The items are stored in a contiguous or neighboring block of memory. So given an array, like A of I denotes like the I plus 1th object stored in an array. And it's I plus 1 here, since computer science, or everything kind of starts in like the 0th base. So so if it like say it's like if it's the 5th index, the A of 5, it actually means like the 6th element or 6th object in that array, right? So just a little quick overview of like a notation here. In the motivation here, like what do we learn about them? It's basically they make up like the basics of like technical interview questions. So yeah, it's really good to know and be fluent in working with arrays. And array also has a lot of operations. So make sure you know how to do that in language. Like for example, one is to kind of instantiate or creating like a new array. And the second thing is second operation would be like actually getting out like an element from the array. The third would be like inserting a new element. And the fourth would be like deleting like a specific element. The fifth operation might be like finding out the size of the array. Six here is iterating through the array. In number seven, it's all kind of bucketed together, but like understanding how to find the min, max, and the sum of the array. The eighth operation would be like how to sort them. Nine, slicing. This is to basically like to get like a subsection of the array. Like let's say instead of like from the beginning to the end, you want like the elements between like the second index to like the fifth index, for example. And then lastly, reversing the array, right? So there are a lot of these operations besides like just the ones that you might use like day to day, like such as creating and like iterating through them. So make sure that you know how to do these things in the language of your choice. All right, and now to kind of like dive into a sample problem. This problem is called pivot index, and this is how the problem goes. So basically, given an array of integers called like nums, right? We want to write a method that returns the pivot index of this array. And what do we mean by pivot index here? So we define the pivot index as the index where the sum of all the numbers to the left of the index is equal to the sum of all the numbers to the right of the index. So, and if no such index exists, we should just return -1. So what this is saying is that basically there's like an index in this array. Though there could be an index, right? It's not a guarantee. There could be an index in this array where all the numbers to the left of it, if you add them together, the sum of that is going to equal to like the sum of all the numbers that are to its right of its index, right? So then, yeah, then the question becomes like, okay, where is that index, right? And if we find it, we want to return that index. And there's nothing that like really fits into that, then we'll just return -1. And then, so there are some examples. So example, we have like this like nums array that's associated with like number 2, 6, 1, 2, 4, 5. These are just some numbers. And then for this question, like we want to be returning the index 3 here, because if you actually go to the index 3, which is 0, 1, 2, 3, and let's see if we add the numbers to the left. So if we add 2 plus 6 plus 1, the sum of like the numbers that are left of this index is equal to 9. And if we also add the numbers that are to the right of the index, 4 plus 5, the sum of that is also equal to 9. Right, so this is why we want to return the index of 3 here. And in this other example, the answer, the nums is instantiated with the elements 1, 2, and 3. But here we want to return -1 because there is just no index that satisfies the conditions that we want. All right, and now this is the exciting part, which is that we are going to start applying the 5 steps approach that Viveka has just kind of like told us about. So step 1, let's ask some questions. And I would like to kind of open it up to everyone again, but what are some questions that you guys might ask as you guys see this problem?
So
Oh.
can we assume that the array will be like non empty, like it'll always contain some like numbers in the array?
Yeah, I mean, for simplicity, you could assume that. And depending on the interviewer, they might say no, like you cannot assume that, in which case you might just write like a simple kind of like a check against that case, right?
Yeah.
But in this case, let's just say, yes, we can always assume that there will be some numbers and it will be an like array of numbers.
Okay.
Is there a size limit to the array?
Is there a size limit? Once again, in this case, we can just assume that there wouldn't be any size. So this could be as small as just like having like one element, or it could be as big as like having like a million elements.
Will the array contain negative integers?
Oh yeah, that's a good question. Let's say in this case, let's also assume that that won't be the case. But that's really interesting or great question to ask, because like having like a negative number might also throw off the calculations as well, right? So
if the array is empty, would we return a -1?
yep, if the array is empty, you can return -1. Although as IO has kind of like raised the question, we're just assuming that there will always be an array of some kind of elements. So yeah, these are some good questions. I'm going to just list some more out here, but look, other good questions to ask might be, hey, like what happens if the input contains multiple pivot indexes? Because that, if that's the case, then it is possible to return like the leftmost pivot index, or like all pivot indexes, or like some kind of like variations from that, from the having that multiple pivot indexes, right? So that might be like an important or like a good question to ask. And in this case, like let's just also make it simple, and like let's say we only want to just return the leftmost pivot index, meaning that the first pivot index that you encounter, you could just return that instead of like having to keep track of like all the pivot possible indexes out there. Yeah, so yeah, but good job on asking these questions. I'm gonna just have listed one more out here. And now let's move on to step number 2, which is let's design an algorithm. So yeah, can anyone also tell us like what could be like a brute force solution here?
So you could visit every element in the array. And when you visit an element in an array, you sum the elements from the start of the array to the current element. And then you sum the elements from after that current element to the end of the array. You compare those sums, and if those sums are equal, then that current element is the pivot and you return that.
Yeah, that's a great brute force solution. This is like basically there what you have described, but what we could do here is like iterate through each index, right, as you were saying, and then just do that calculation for each of them, which is then calculate the sum of all the elements to the left of it, and then calculate the sum of all the elements that are right of it and compare them. If they're equal, you got the pivot index, just return that. If not, then we'll move on to the next element and do the same process again, right? Yeah, I'm also kind of curious to hear that is like a valid brute force solution, but any thoughts about what the runtime of that would be?
N squared.
Oh, n squared. Okay, can you elaborate on why that might be the case?
Because you need a nested for loop.
You need a nested for loop to do, okay.
Is it because you're iterating for the first sum on the left side and then you're iterating for the other sum on the right sum? Or sorry, other sum on the right side?
Yeah, I mean, you guys have like, both of you guys have like the right intuition here. Is that there's kind of like the step to find the sum of the left sum and right sum. That needs the iteration to like each one of those elements, right? And then so in the worst case, like you would have to like add up like n elements, right? I mean, by definition, this array, we're assuming that it has size of n. So the worst case is that we're adding n elements, and that could just like be divided between the left side and the right side, or it could just like all show up in one side and nothing on the other side. But the worst case would be still like n, and the summing process will be finding the sum of that will be O of n, because you need to iterate through them, right? So that's the n part, and the intuition around the nested loop is also correct in that in the worst case, then you have to kind of do that n times, right? Because you're basically trying to find the sum for each element, for each like pivot index in the array. So in which case you'll be kind of trying out like all of the different possible like elements. So that's the kind of like outer for loop part. So that's why yeah, you could end up with well, this brute force solution would be like O of n squared. So yep, you guys got it. Now I'd like to kind of ask you guys, what would be a more efficient solution here? And by more efficient, we mean what kind of solution would be able to run this faster than O of n squared? Any ideas, clues, thoughts?
I don't know if it. Oh, sorry.
Sorry, I was gonna suggest like having the sum of the whole array first and then subtracting as you move through the different integers through, and then like yeah, I don't know if, well, no, I don't think that would make sense. Sorry.
Oh, no, Valerie, I think you're definitely onto something here. I'd like to kind of like, understand more of like the ideas that you had, but it sounded like your idea was to find the sum of like all the elements in the array first, right? So if you know sum of like all elements first, what can we do with that?
So if I have the total sum, I was thinking of having that as an integer and then going through, iterating through it again, but now keeping the right sum and also subtracting the total sum, I guess. And then comparing the two to see if they're equal at any point.
Yeah, that actually sounds like a fantastic idea, because once we know what the total sum is, right? That would take like basically a single pass or single iteration against the array first. But in the second visit, what we could do is, yeah, we could just calculate the sum of the left, make it what we call just like the left sums, right? Like basically sum of all the elements to the left of the pivot index. But we can only calculate that. But because we know the total sum, as long as we know what the total sum and the left sum is, then we can also find out what the right sum is by doing like this simple subtraction, right? We could do total sum minus left sum minus whatever the value at the pivot index, whatever like the difference that comes out after that subtraction is going to be the value that represents the right sum. Right, Valerie, that's the idea that you're trying to shoot for?
Yeah, that's what I was thinking.
Yeah, and that sounds great. And we'll see why that would be a more efficient solution. So yeah, so Valerie was I think she was able to find this kind of relationship between the sum of numbers to the left of the pivot index and the sum of the numbers right of the pivot index, right? And that relationship is basically this, which is the right sum is equal to total sum minus left sum minus like nums at index I, which is basically the value that's being represented at the current index. And this is kind of like an important fact to know, because what it's saying is that if you know the total sums and the sum of the numbers that are left of the index, or for simplicity, just call it left sums, then we can definitely know what the right sum would be. So basically this is going to be faster because the first pass to find the total sum, what is going to be the runtime of that?
It'll be linear.
It'll be linear. Yep, O of n, because all you're doing is just adding those n elements together, right? And in the second pass, as you're kind of iterating through the array again and calculating, what the left sum and the right sum would be, what is going to be the runtime of that?
It's still linear.
Yeah, it's a linear, except you do have to be a little bit clever, right? Because as you iterate through each index, and you can call like sum operations again and again, like you could still like kind of end up like imposing like another linear runtime in that in a loop. But what we could do is we could just like keep this like running sum, right? That could represent the left sum. And by running sum, what that means is you could just declare like a single value that represents like left sum. And you could just like keep updating that as you go along in your search for a pivot index. And if you do that, then that's pretty clever because you don't need to like, do the sum operation again and again. All you're doing is you'll be adding like one element to that like running left sum, and then doing like another operation of subtraction to like find out what the left sum is. So that, that subtraction would also be like a constant time operation. And this comparison of like the left sum and the right sum would also be like a constant time operation. So it's really clever because this kind of like the first pass to like calculate the total sum, and this like iteration to the second pass to iterate through the arrays again, that's going to be linear, and that's going to be like inevitable. But then as long as you kind of keep that operation inside into like constant time, then you could just get away with like 2 of like linear runtime process, and overall runtime was to be O(n). So that's the high level idea, but we're going to kind of get into the code of it. So this is just an example, but total sum would be sum. This is like kind of like in the Python pseudocode, but we just call it sum operation and run the nums, and that will give us this like total sum back. Just one call out here, just because like you see like a single line here without any operation, don't fall into the trap of thinking that this is a constant time operation. Even if your language of your choice, like such as JavaScript or Python, has like this like sum operation underneath the hood, it's actually kind of still iterating through like each element. So that's still like O(n) runtime. So after we find out what the total sum is, we then declared like this kind of like one single variable that represents the left sum, and we initialize it with 0. And then what we do is we iterate through the nums again, or the arrays again for the second pass. But for the second pass, what we do is, okay, we're basically kind of like comparing the left sum against the right sum, which is kind of calculated through the subtraction, which is this subtraction is also a constant time operation. And when that's equal, then that index I is going to be your pivot index, and we can return it. Otherwise, you want to move on, but before you move on, you want to update the left sum, because now the left sum is going to be equal to that whatever left sum that you had added with this element x. And otherwise, if your code can't find this pivot index, it would just return -1. Darren, I saw that you raised your hand.
Yeah, I wanted to be clear. So is I the position and X the value of the position?
Oh, yep, that's the yep, that is correct. Once again, this is in Python, so it may look different, in the language that you work in. But at least in Python, enumerate is just kind of like a native like operator that you can call against your iterable, and that would kind of give you just like pair of the value back, in which like the first one would be your index, and then the second value would be the value of that element. So it's kind of like a simpler way to do it, in compared to just like just declaring an index and then finding out the value by like indexing into that array to find that value. This kind of gives me both values back at the same time.
Is it a typo? Is it supposed to say if the right sum is equal to total sum minus left sum minus x?
This is no, this, so you're talking about this subtraction here?
Yes.
Okay, no, this is not a typo.
Oh, that total sum minus left sum minus x is the right sum, right?
That is the right sum, yeah.
Okay, yeah.
So another way to write this is that I could have just brought this subtraction into another line and just redeclare as like a right sum and just compare if left sum equal right sum, right? But this is this subtraction, yeah, does represent that right sum. Yeah, any other questions? All right, so this kind of like wraps up our kind of like the lesson for today, but here's some like links to other practice questions that on like the website LeetCode. So yeah, I would definitely encourage everyone to check it out and get more practice in. And feel free to like, work on any of these problems with some mentors. And or even you submit your solution in one of the Slack channels. Yep. Any questions before we wrap up the lesson for today?
Yeah, I had a question. So sometimes, like in Java, there's a sorting array function that is built in. And I was wondering if we need to know what the runtime for that is. Like if we use it when we're like in an interview, do we need to know what the runtime is for built-in functions?
Yeah. Becca, do you want to take on that question?
Sure. Yeah, I would say if you're going to use any library functions, it is important to know because that will factor into the runtime of your algorithm. So I would say, yes, it is important to do that. So I would just check for Java search, like you can just Google like Java search, search array, or sorry, sort array built-in algorithm runtime and see what comes up. I will say, I think the majority, we'll get into searching and sorting later on in the program. But if I remember correctly, I think the general kind of average fastest sort or sort is n log n time. So I think you could also say like, okay, I'm going to use the sort. I'm going to assume it's n log n here and use that to factor in to your algorithm's runtime. And of course, you want to make sure that's like accurate. And n log n is like a reasonable sort runtime. You wouldn't want to say like, oh, I'm going to use this function. I'm going to assume it's constant because that is not going to be as accurate. So you want to make sure it's reasonable. And you can definitely use those functions that are built in. Depending on the interviewer, sometimes I know, for example, Python has a lot of really fancy functions you can use with sets and things. And I've had friends who will use those. And then the interviewer might say, okay, that's great. That solution works. Can you please code it without using those functions? So something to keep in mind, especially if like Wento pointed out, when he used that sum function, that would probably be like a couple lines to write out your own sum function that goes just to one. So sometimes if you were using a library function that actually encapsulates a lot of the logic that the interviewer might have actually wanted you to write yourself, they may say something, but you can always ask to be like, I'm going to use this function. Is that okay? And they might just check your knowledge, be like, okay, do you understand what this outputs? Do you understand the runtime, those things? So as long as you have that, you can always ask.
Thank you.
Yep. So yeah, that's a good question. Any other questions about today's lesson content? If not, just want to
Actually, I have one.
okay.
So what if you are unable to think of a more optimized solution after coming up with the brute force?
So your question is, what if you're not able to come up with a more efficient solution?
Yeah.
In that case, I would try to have a conversation with the interviewer. It's like you can say, hey, like I think I have the solution for the brute force solution. However, I'm having trouble coming up with a more efficient one. Would you like me to like spend more time trying to come up with a more efficient solution, or just implement this brute force solution, right? because I think just having that conversation with the interviewer is going to be key, because depending on what your interviewer wants, like, they might just want you to like see how you code out the brute force solution, and that might be actually be okay. Sometimes, that is not like, that is not what the interview is looking for, and the interview is trying to look for your more of the thinking skill. In that case, like they might be like, well, I would like you to spend more time thinking about the more efficient solution. And if you're really struggling, some interviewer might like start to give you hints, or if you're really struggling, you could also like ask for hints yourself, and try to see if you can come up with that.
Yeah. Another quick thing to add on to that, if you're struggling, optimization is hard. And I think some of it comes from practice and recognizing certain patterns. Like, for example, if you have like an n-squared solution, thinking about, oh, maybe I have two nested loops. Do I really need both of those loops? Looking at those different pieces there, or look at, and of course, this can be time or space that you're trying to improve upon. The interviewer might tell you, or you might say, oh, I think I can improve here. So once you do that complexity analysis, that can help you to think, oh, where should I optimize this, or where can I optimize this? And as you practice, I think sometimes there will be kind of things that align better. So you can ask, another thing you can ask kind of more pointed hints, like Wenta was saying to the interviewer, like, okay, was it more important that I optimize for space or time? And they might tell you, they might say it doesn't matter, they might tell you, and then you can focus in on one of those things. So if they say make it faster, but we don't care how much space you use, okay, maybe another data structure to help you hold the data in a more useful way is going to take more space, but might improve your time. And that you can kind of use that to narrow down your options.
Okay, thank you.
Another good question. Any other questions? Not, I just want to spend 2 minutes just raising awareness about these helpful resources. So we do have like some kind of like more like a complimentary slides on different like small topics. So there's one on array operations. These are mostly written in like a Python pseudocode, but feel free to check them out and see, like, yeah, if you actually know how to do these like operations in the language that you work with. So it kind of goes over those like 10 operations on array that we have like earlier mentioned. And there's another slide. This is just like helpful to know, not just in an interview setting, but in terms of like your software engineering like skills and career. Is like basically kind of goes over the different coding principles that would teach you how to write good code. And by good code, it's like easy to follow and maintain. So I'll definitely like encourage like everyone to also kind of go through it all in your free time and try to see if like any of these like things that is something that you guys are already doing, or if not, just picking up on them so that so that your code will be will be easy to read and maintain. So yeah, quick call out here in terms of array operations and coding principles. And we do also have one more announcement, right, Viveka?
Yes, we will be introducing a kind of supplementary speed mentoring program into our program, sub-program, I guess. But basically, keep an eye out for in email or in Slack, where basically we are giving the opportunity for all you fellows to have an extra session with another mentor that is not in your pod. So if you're interested, we'll be sending out a form so you can fill in if you'd like, and it'll probably be, we'll pair you up with another mentor and let you set up maybe like 30 minutes to chat with them as well. So keep an eye out for that if you're interested. Yeah.
Yep. Thanks for the announcement. You guys should definitely sign up since it'll be fun to meet other people in this program. But other than that, I think we're done for today. Thank you guys so much for attending today's lesson. There was great participation all around, so kudos to you guys. And as always, like please look out for the recorded lessons and the slides, both on the Slack channel as well as like email for your review purpose. And anytime you have questions, just feel free to reach out to us or your mentors. Thank you guys so much, and I hope you guys have a nice rest of the weekend.
Thank you.
Thank you.
Thank you.
Bye-bye.
Yeah.
All right, thank you.